Now let's explore how we use GIS to analyze geospatial data. And let's do it within the context of a geographic information system, in which geographic features and attributes form information that we analyze within a system like ArcGIS Pro or QGIS. We'll start by focusing on the basic geographic units that support geoanalytics. Now, some of these you've heard before, like features, cells, and triangles, but others, like clusters, bins, cubes, and voxels, may be new to you. Features, or points, lines, and polygons, cells, and triangles with attributes, are the basic geospatial model that we use in a geographic information system. And which model we select depends on what we're trying to accomplish. Vector data is really great for discrete data sets. For example, like modeling hydrographic features like a lake or a stream. Raster data is great at representing continuous phenomena like land cover. In this case, for example, grass or water. Last, triangulated data is great at representing elevation or concentration. In this example, where and how much water might flow over a surface into a nearby stream or lake. Now, as geoanalytics has evolved, we've responded by introducing new geographic units that we can utilize to perform more sophisticated analysis on very large data sets. Clusters, or clustering, is when nearby point features with attributes are grouped into one point with statistics. Clusters visually and statistically summarize large point datasets as points while masking individual locations. And so sometimes when you have a point dataset with 1,000 or millions of points, you really can't see the forest for the trees. And so we use clusters to visually generalize the datasets to make them a little bit more accessible and the ability to see trends within the data. But clusters can also be used to mask individual locations, and this might be for privacy purposes, or it might be, for example, a citizen science project where the underlying quality of the individual data points are not as valuable as the aggregate. Now, the more clustering you use will group your points into fewer and fewer features, and clusters can be proportionally sized by group feature count. In the animation that you can see on your screen, we start with a number of points that represent power plants and type in Europe, and then enable clustering. And that takes the points, clusters them into both different colors representing the different power plants, but also different sizes representing how many power plants are in that cluster. So clusters are really good for complex point data, dynamic data, and for example, social media data, where you have thousands, if not millions of points that are changing often, and you want to analyze almost in real time. We use bins to group point features with attributes into a polygonal framework with statistics. It's very similar to clusters, in which we visually and statistically summarize large point data sets, but this time, instead of clustering points, we summarize those large point data sets as polygons that allow us to mask individual locations. So bins are just a collection of polygons arranged in a framework that are created through tessellation. And there are a number of ways to represent bins, including, for example, square, hexagon, transverse hexagon, triangle, diamond, and even circles. Now, bins can be fixed or dynamic. The image that you see on the right side of your screen represents static bins. So when I'm zoomed out on South Carolina, the number of circular bins that I have are the same as when I zoom all the way in on South Carolina. Dynamic bins allow you to show a larger number of bins when you're zoomed out and a larger number of smaller bins when you're zoomed all the way in. So it's really great for interactive mapping. We use bins for citizen science, for example, demography, especially if we're trying to mask the underlying data, or weather, where we might have thousands and thousands of data points that provide us with temperature, but we're most interested in the overall trend and not the individual data points. Cubes are a 3D collection of square bins with values arranged in a cube with statistics. We use cubes to visually and statistically summarize spatiotemporal data. That's data that has an X and Y spatial location with T time. And so each bin represents a location and value that occurred in time. And if you look at the graphic in the bottom middle of your screen, you can see a diagram of a cube in which individual bins are stacked together to form a cube. And notice that the cube is located at an XY location over time. So any one column of bins is referred to as a time series because it shows that location and how the values change over time. Or a time slice where you're looking at all the bin values across your mapped extent for a particular time. Now, space-time cubes are very similar to a common government format called NetCDF, or Network Common Data Format, that stores data in arrays of stacked raster data sets. And matter of fact, the visualization that you see in the lower right-hand corner is less common way to visualize cubes. Cubes typically aren't visualized in 3D like this with all of the data stacked on top of each other. Typically, you visualize it as a single raster data set that's filtered for that particular time. Or you might create an animation to view an event over time. In the example in the lower right-hand corner, this is showing earthquakes that occurred in Australia over time, or you could imagine an animation where you're looking at a major rainfall event for a hurricane in the United States. So cubes are really great for climatology data, meteorology data, hydrography data, any data set where you have a lot of continuous data that changes over time. The last type of basic geographic unit that we use for geoanalytics that I'd like to introduce to you are voxels. Voxels are 3D collection of square bins with multiple values arranged in a cube with statistics. And so they visually and statistically summarize multivariate spatiotemporal data, which includes an X and Y location, a Z, which is another variable, which may be elevation, and T time. So each bin represents a location and value or values that occurred over time. So a voxel is really a space-time cube plus at least one additional variable, and they're really great for very complex continuous data sets that have a lot of variables associated with them, like groundwater, air pollution, oceanography. And if you look at the diagram in the lower left-hand corner, you can see that you have a voxel that is arranged in space in XY over Z. In this case, that might represent elevation. And then that same location is represented over time, as diagrammed here as T1, T2, and T3. And in the animation in the lower right-hand side, I'm not exactly sure what this data is showing, but I can see that it's voxels that are categorized by color and mapped by location and depth in 3 dimensions.